So welcome to today's Micron webinar that will cover data manipulation in artificial intelligence world. I would encourage you to ask questions as presentation is happening. Please ask your question through the Teams chat function. And then once presentation is finished, Esther will try then to answer those questions one by one. Anyway, Esther, over to you.
Thanks, Miodrag, and good morning to all of you that have attended, that are attending. Thank you so much for joining us. I hope I'll be able to share with you some insights into the artificial intelligence world and how that is related to memory and storage. My name is Esther Spanger. I am responsible for Micron business development, specifically with a focus on the enterprise in the channel. I have about 25 years of industry experience in a variety of roles for the last 4 years with Micron, focusing on business development. So what we're going to talk about today is, first of all, I want to kind of share with you some of the, the terminology and the things that are associated with artificial intelligence. And, when you're looking at artificial intelligence, what it really takes to actually implement a solution like that. Of course, we talk a lot about the role of memory and storage, since that is what Micron is, manufacturing. And then we'll get into an even deeper, a dive into particularly the configurations of both SSDs and DRAM modules in AI optimized servers. As Miodrag was referring, if you have a question, feel free to put it in the chat and we'll address that either during the presentation or towards the end. Okay, so when you're looking at artificial intelligence, right, the main key or the main basis of any artificial intelligence implementation is data. And, you need lots and lots of data in order to build any kind of AI engine. This particular image, by the way, was generated with AI. And so for us, it is really all about the data. How do you manipulate the data? How do you, store the data? How do you, transfer the data? And how do you eventually, of course, utilize that into an AI engine? And so there's kind of two key AI implementations at the moment. One is called generative AI, and the other one is predictive AI. Their implementation and kind of the output of what they're providing is slightly different, but the core of each of these two AI methodologies is still based upon lots and lots of data that needs to be fed into the AI model. So generative AI, I think, is something that we've all become very familiar with recently through ChatGPT. That is the AI implementation that creates new content, whether it's images, text, video, and even, it can start to write code based upon the input of a user. On the other hand, predictive AI is really looking at historical data and then, predicts an outcome for future data. So an example that I will use a little bit later on in this presentation, it is being used for cancer research or doctors, diagnosing images of cancer and understanding, what the diagnosis is for that particular patient. So of course the AI engine had to learn hundreds of thousands of images in order to understand, what a cancerous image looks like. And so when there is a new image being fed into it, the AI engine can then predict, whether that image will most likely have cancer or not. So that is really a good example of predictive AI. But regardless of whether what is predictive or generative, we really starting to see a lot of implementations in our world, both in the near term and the long term. And so I try to kind of split them out into, these three different segments. What can we expect from AI in the next few years? What can we expect it in the medium term and long term? And so, we talked a lot about autonomous driving for many years. I think that is still, that is still being, not widely adopted for the sheer reason that, it wasn't as flawless as everybody thought. But it is believed that, the new AI engines and technology are really going to enable autonomous driving. Similarly, healthcare. We talked about an example of radiology scans and cancer detection. Healthcare, there is, a lot of different implementations that can really utilize healthcare. Video training, we can create digital avatars that, will guide us through different videos. Of course, that's a great example. And then, law enforcement, when you're looking at, video surveillance and, kind of creating all sorts of AI engines based upon, that video surveillance. So some medium term, long term, you can think about, home assistant robotics, even battle bots and AI enabled warfare. How can, AI, they can predict where, the next, where the enemy will strike next, etc. And then, of course, the new hire, is AI truly going to take over us, as human beings? And what part of our work will they be able to take over? So there's a lot of different developments in AI, but the key of it all is that all of them need tons and tons of memory and storage. So when we're looking at an AI implementation, there really is multiple stages that you need to think about of, before you actually can build an AI model and an implementation. And so we try to, in this particular slide, I try to split it into these three different pieces. First of all, the amount of data, right, that we need to build our AI engines need to be captured somewhere, right? We have many ways of capturing data in our everyday world, whether it's, through our manufacturing processes, through our phones, through sensors, etc. There is, a lot of data that we need to capture in order to eventually feed that into the AI machine. So there is a gazillion different sources that, depending on the implementation, we can pull from. Once we have all that data needs to be organized. You cannot just, get, a random bulk of data and, feed it into the AI machine. We actually, need to find a way to label that data, prep that data, etc. So there is a certain part of the AI implementation that requires organizing of the data. And then finally, we're looking at the utilization of the data. This is really where, kind of the interesting part starts, at least for me, where you're looking at, the training models and what we call inference models. So this is really the part that happens in the data center. This is where we need, AI optimized servers. And this is really where we start looking at all of this, memory and storage. Now, for the other stages, there is certainly memory and storage needed. Organization typically is done in the edge, and the capturing, of course, is done in the devices that are closest to the data source. But for today's discussion, I want to focus primarily on the training and inference clusters that are located in our data center and what we need to do to really optimize these engines. So when we're looking at, these training and inference clusters, just a kind of a definition of what is the difference. When you're looking at the training, this is really the part where the AI model is taking large data sets and, start to train the model to recognize patterns and eventually, right, generate new data. So this is where you need to have lots and lots of data, and that data needs to be going through that AI engine, meaning you need a lot of fast memory and a lot of fast storage so that the model can learn the data as fast as possible. Now, inference, on the other hand, is once you already have a model built, this is when you're putting new data into the model and asking the model basically what the outcome is of that new data. So for example, when we talked about the the cancer diagnosis, you would feed the model a new image of the patient that the doctor is working on, and the model will then predict what the level of the cancer is for that particular image. So that also requires a lot of memory and storage, but probably not as much as the part on the training side, because with inference you're only utilizing one new piece of data, and you already have a model that was generated. So typically AI servers that are optimized for training sets are substantially more heavy on memory, storage, and GPU. Um, AI servers that are more focused on the inference part of the implementation are typically less heavy on GPU storage and memory. So we talked a little bit about this AI example, in this case the predictive AI example, right, where the hospital needs to build an AI infrastructure so that they can do better cancer diagnosis via that medical imaging for the hospital. So when you're looking at the training and the inference piece of it, right, the training is to scan hundreds of thousands of in this case, right, x-rays of lungs of people to teach the AI model which of these images, contains some kind of tumor, and which ones are, regular healthy images. And that training requires, therefore, lots and lots of computational capability, right? You need a lot of GPUs, you need a lot of fast storage, because you need to feed the GPUs with a lot of these images, and of course you need a lot of memory, because GPUs are very computational intensive. Now, once you have the model, the inference piece is really what is happening when the doctor basically enters the image of the patient that they're working on at the time, and will basically ask the AI model, is this what is this image, does it contain cancer or not? So you can see that once the model is built, it is a lot less computational intensive and storage and memory intensive. It just needs to utilize the algorithms that were already built during the training. But that really is the difference between training and inference. One is to build the model, and the other one is to, if you will, utilize the model once it is built. All right, so when we're looking at the AI and the memory and the storage that we are utilizing in an AI implementation, there's really different layers that we can use. I assume you may have heard about high bandwidth memory. In fact, Micron yesterday announced that our high bandwidth memory 3 was released. This is a piece of memory that is typically incorporated very closely onto with the GPU, and it is typically part of a motherboard that you already buy in the entire server. So when you're looking at a configuration of a server that you already of a motherboard that basically is already part of the motherboard, so typically a system integrator or channel customer doesn't have the ability to choose the capability of the high bandwidth memory that is already incorporated in the type of AI server that they're buying. Where they can influence, what they can choose is the configuration of either the main memory, the SSD data cache, or the networked storage that they can potentially connect to that AI server. So as you're going up in this pyramid, if you will, the cost of your storage and server goes up, and your bandwidth goes up. As you're going down, you're getting more and more capacity, but lower and lower latency. So it really depends, again, what the exact implementation is that your AI implementation and infrastructure requires, but these are high level the options that you can implement in your overall infrastructure. So let's look a little bit about the AI servers that have been shipping in the past few years. So according to one of the analysts that we're using, called TrendForce, they state that in 2023, 8.8% of all servers in the industry were shipping as an AI server, and that is growing to 12.1% in 2024. So a massive growth specifically for the AI segment of the server market. And, that is really where all the hype is. And again, that is really where we are focusing our discussion on today. So remember, we were looking at the only on the training and inference clusters that we are running into our data center. And so when we're looking at the different options for training and inference clusters utilizing Micron products, there's basically different flavors of SSDs and DRAM that can be utilized. And I'm basically going to walk you through each of these different configurations and what they are optimized for in these different server models. So starting off with, the top part here, you see a high density AI optimized server that has a lot of GPU capability. Therefore, it needs to have a lot of very fast storage capability and a lot of DRAM. So typically these very heavy GPU heavy servers are the ones that are used for training purposes, because they have this huge amount of data that needs to go through the engine. You have more in the middle general purpose AI servers where the ratio of GPU to SSD is quite different. These are the kind of servers that are typically used for inference, and then remote data storage is where you are putting all of that data that you need to run through your model on a networked, high performance storage. So let's look at each of these individual configurations and look at them a little bit more in detail. So when we're looking at these very, very AI optimized servers, very GPU dense, the key component from an SSD perspective that would be the best implementation for that very heavy GPU server is our very high performance NVMe product, what we call the 9400. This is really, the fastest performing SSD in the market. You can utilize it as a very, very large local storage cache that what you really are after is making sure that the GPUs that you have implemented in your server are not sitting idle. GPUs are certainly the most expensive part of your AI server, and so ensuring that they can run and build that model as much as you can, as quick as you can, requires very, very fast storage. And so the 9400 is currently one of the fastest SSDs on the market today, which really would be the right implementation for a GPU heavy AI server. Again, this is really meant more for the training part of the model, of the AI implementation, where you're trying to scan, right, hundreds of thousands of images to build and train your AI model. So high performance, high capacity NVMe storage would be the right fit here. Moving on to kind of the general purpose AI server, or the one that we typically would use more for an inference kind of implementation, meaning the AI model was already built, but now we basically want to utilize the model and provide it with a new image, and let the AI model determine if that image contained a cancerous pieces or not. So in that case, you probably need not as high performing SSD, still very good performing, but not, like the Ferrari of the world, if you will. So we typically recommend for these implementations our mainstream NVMe, so the 7450 or a newer version that we recently released is the 7500. That NVMe implementation really enables you to get, the most optimal cost performance and capacity balance in your server. There's not as many GPUs typically in these servers, and so therefore a more moderate SSD capability will be good enough for feeding these GPUs. So in this case, the inference part of our model will be, supported by a mainstream NVMe. And then the last piece, the remote data storage, is that we are going to talk about, is really when you need to have all of these hundreds of thousands of images, you need to store them, and you need to be able to pull them off from that storage in as fast a way as possible, so that you can feed that into your AI server and not have your AI server sit idle. So in the past, typically these network storages was based upon hard disk drives. We came up with a very high capacity SSD, which is quite mostly read intensive, and is lower cost than your typical SSD. And so by providing very fast storage but for more moderate cost, you can replace your hard disk drives and get to a situation where your GPUs are not sitting idle. The challenge with a hard disk drive based implementation is, while they're lower cost on the storage side, but if you cannot pull the data fast enough from these hard disk drives and have your GPUs sit idle, then you're basically paying for a solution that is probably much more expensive, because your GPUs typically are the most costly piece of your infrastructure. So replacing those with very high capacity, low cost SSD storage makes a lot of sense to optimize the cost of your overall solution, because the GPUs will not be sitting idle, and potentially you could even implement less GPUs. So that is, in a nutshell, the overall portfolio for AI service from Micron. There's really, three NVMe product lines that we are supporting: a high performance product, a mainstream NVMe product, and then a high capacity NVMe product. We also have a SATA product, but typically that is not really being used in an AI server. That's really typically only focused on NVMe based products. So this is the entire portfolio that you can utilize from Micron. Moving on to DDR5, and what the trends are on the DRAM side for artificial intelligence based servers. Obviously, when you're implementing AI in your server, you are going to run a very high performance workload, and also probably, you have a lot of DRAM that is required. And so what are the implementations or the configurations that you need from a DRAM perspective? So when we're looking at, getting more and more performance out of our AI servers, right? The first thing that you will see is that these servers are going to run or utilize CPUs that have more and more cores in each CPU. This graph shows you the trend of the different, CPU manufacturers and the maximum cores per CPU that they're bringing to the market. More cores per CPU means that you need to have more bandwidth, memory bandwidth, sitting behind these CPUs in order to make sure that these CPUs can actually run the code. If you have a lot of cores, but you don't have memory that sits behind the core, then you're basically having something that cannot run. So the push to get more and more bandwidth from your memory is definitely a large driving force in the market. So when we're looking at the two key CPU manufacturers and the platforms that they're bringing out in 2024. We're seeing, for example, Intel. There are two key platforms that are shipping this year. Sapphire Rapids and Emerald Rapids are, really the two main ones. From a bandwidth perspective, the DDR5 bandwidth, the majority of their motherboards are going to ship based on either 4800 or 5600 speed DDR5. And then later this year, when they're coming out with the Sierra Forest and the Granite Rapids platform, we also start seeing 6400 based speed. Now, AMD is going to stick primarily to 4800 speed this year with these three platforms that they have released and that are shipping. And then towards the end of the year, when they come out with their Turin platform, you see that also they will start transitioning to the higher capacity, the higher performance, speeds in DDR5. So from a memory manufacturer, we need to be ready to support all of these platforms and their speeds. And the slide that you're looking at is the actual Micron DDR5 portfolio. And, in a nutshell, what it means is that regardless of the speed of the CPU requirements, we have everything released and are available to support any platform that is going to ship in 2024. We will have also 6400 based products coming out in the second half of this year, and so we are very much aligned with what the CPUs are going to demand towards the end of 2024. Now, one of the side effects that we're starting to see in the industry as we're moving towards higher cores, because we need more performance. More cores, we know we need more bandwidth per core, right? We're transitioning from 4800 to 5600 to 6400. But one of the side effects that we're seeing as a result of that is that customers also start to buy a lot of DRAM capacity that they don't necessarily need. So when you're pushing for a lot of performance, you need, these cores, you need more bandwidth, but you don't necessarily need all the capacity that sits, behind these cores. So when you're looking at the standard capacity points of DDR5, 16, 32, 64, 128 gigabyte, these are all binary capacity points. And the challenge is that, when you need to put all of that capacity behind your cores because you really needed the bandwidth, you may end up buying a lot of capacity that is not needed. And this is what we call stranded capacity. And so this is really coming from the hyperscale world, where you can imagine if a Google or an Amazon has hundreds of thousands of servers sitting in their data centers, that they want to optimize every gigabyte that they're buying and not overpaying for something. And so what the industry has come out with is these what we call non-binary capacity points. And so this is really a way to find the best configuration and the best optimization between the amount of cores you need, the amount of bandwidth you need, and really the amount of capacity you need, and don't overpay for capacity that you don't really need. So it just allows a more granular, if you will, configuration. You don't have to jump now from 16 to 32 or to 64. You can actually, take 24 gigabyte or 48 gigabyte as points in the middle. And when we look at the trend in the industry, the graph on the right hand side shows the trend from an analyst that we call TrendForce. And you see that these non-binary capacity points are starting to make an inroad into the server DIMM shipments over worldwide. So that's really the result of the push for more and more bandwidth, but not necessarily more and more capacity. Now, on the other hand, we are seeing certain implementations of the AI world, wanting to have as high capacity as possible. This is the push for 128 gigabyte and beyond is there now. There is today 128 gigabytes DRAM on the market for very, very high cost. If you want to buy today a DDR5 128 gigabyte module, you're probably going to be paying between $1,500 to $1,800. At the moment, Micron does not support 128 gigabyte. We will only have that in the middle of this year. And the primary reason for that is that in order to build today 128 gigabytes DDR5, you need to have a very complicated manufacturing process where you stack multiple pieces of silicon on top of each other. Micron purposely decided not to go there, as we only want to have one layer of silicon in each of our chips. And if you do that, you get to a maximum capacity of 96 gigabyte. Our competitors decided that they do want to build modules that stack multiple layers of silicon on top of each other, so that they can reach the 128 gigabyte. It is a more complicated manufacturing process, hence the very heavy price tag that you see in the market today. We are only going to come out with 128 gigabyte once we're able to build a module using only one layer of silicon. So that means that we are waiting for our next generation DRAM technology, which is going to be coming out very soon. So that is the push for the high capacity, what we call, so SDP stands for single die packaging. From Micron, we will only build products using one layer of silicon inside our chips. So today we can get to 96 gigabyte, and by the middle of the year we can get to 128 gigabyte. And that really is the story for the DRAM world in AI servers, the push for more and more bandwidth and the push for higher and higher capacity. And that is really what we're continuing to support. So when we're, overall, the market in the artificial intelligence, data center is going to be very, very hungry for more DRAM and more NAND. We see the average capacity of DRAM in an AI server. These large GPU optimized AI servers can be up to 8 times the DRAM and up to 3 times the NAND compared to a typical general purpose server that we are seeing in the market today. So there is a huge growth and drive for higher capacity, faster storage, and more of it inside a server as we're seeing the AI market take off, and that is really one of the driving forces in the market today, and one of the reasons why we see our market growing for the next few years without any real limitation. And that is everything that I had to share with you for today. We actually have a specific website, learn more at micron.com/AI. If you want to learn a bit more, of course, you are also free to, ask any questions right now. And Miodrag, I will revert it back to you.
Thank you, Esther, for this presentation. So let's see, let me check, do we have any questions? I don't believe we did. I was keeping an eye on it. So I think if there are no questions, I think this should then conclude this webinar for today. Esther, is there anything else you would like to add before we finish?
No, I hope it was useful for everybody, and again, feel free to reach out to me if you have any additional questions.
All right, thank you, Esther, and you have a nice day, and hope to talk to you this afternoon again.
Yes. Okay. Thank you so much.
Have a nice
Bye-bye.
day. Thank you.
Bye-bye.
Bye. Bye.